Alrighty, so hello and welcome back from spring break, and yeah, there we go. Spring break. I am on my way to recovery. Symptoms are mild. Thank you for everyone who sent. There were quite a few really kind emails. If I seem chipper for having COVID, I just woke up from a 3-hour nap because I taught this morning, and like I said, symptoms aren't too shabby, but the fatigue at this point is the biggest thing. So you teach in the morning, nap in the day, and then do the second half. Anyways, okay, so we're gonna go ahead and dive on into it. I'm sure there are questions about the exam. Let's save those for lab tonight. There is no lab assignment due tonight. I posted about that already. But I can also answer any further questions you have about the test during that time, and you can attend regardless of which section you're enrolled in. So we're going to today start our discussion of chapter 6. Chapter 6 is going to be about, we're going to discuss phases of matter. Excuse me. Spend a decent amount of time on gas laws, and also talk about phase changes. So anyways, let's go ahead and dive in. So also, I apologize just in advance if I still have a bit of a cough, so I'll try to not. But if I do, I'll mute the mic so it doesn't peek you guys out. All right, so we're going to be talking about the phases of matter: solids, liquids, and gases. Definitely an emphasis on gases. But before we start talking about the individual phases, we need to kind of establish a more general theory of matter itself, and this is known as the kinetic theory of matter. The kinetic theory of matter. All right, now, the word kinetic itself means motion, all right? And so when we talk about, for example, kinetic energy, when we're talking about kinetic energy, we're talking about energy that's associated with motion. All right, energy associated with motion. All right. And this is contrasted with potential energy. All right, potential energy is energy associated with excuse me, position or composition. All right, so examples of kinetic energy would be heat, um, potential energy. In a chemical context, excuse me, is often associated with bonds, um, right, or the actual what matter is made of. And again, when we talk about the energy associated with bonds, we're talking about stored energy. And when we talk about heat, we're talking about moving energy that's in motion. Right, so when you touch something and it's hot, that is literally energy moving from the hot thing into your body. So that's why we say, when I say heat, I'm talking about energy that's moving. All right, now, now I want to focus on the concepts now that we've kind of had this, kind of set the groundwork, laying the foundation for kinetic versus potential energy. I want to talk about the concepts for the kinetic theory of matter. All right, we're not going to get into all the technical definitions. I more want to just talk about the broad, kind of focus on a broad understanding of what's involved with this theory. So the first thing in the kinetic theory of matter is that all matter is in constant motion. All right. Something to realize is this includes solids. All right, all matter, including solids, is in constant motion. The amount, oops, sorry, I want that in pink. The amount of motion and kinetic energy, for that matter, is determined by the phase of matter. All right, so all matter is in constant motion, and the amount of motion and kinetic energy is determined by the phase of matter. So, for example, the energy of the solid phase is less than the energy of the same substance in the liquid phase, which is less than the, and actually, I should put K's in front of this because we're talking about kinetic energy. All right, so the kinetic energy of the solid phase is lower than the kinetic energy of the liquid phase, which is lower than the kinetic energy of the gas phase. All right. So that's the first thing is if you're a substance in the gas phase will have more kinetic energy because it's in greater motion than the liquid phase, which is just sloshing around, which also has more kinetic energy than the solid phase, which is kind of like frozen. Well, solid. So that's the first principle of the kinetic theory of matter. The second one is all matter experiences attraction and or repulsion with other matter. This is another way of saying that all matter has potential energy. Which I'll abbreviate as P. KE is kinetic energy, PE potential energy. The fact that all matter experiences attraction or repulsion with all other matter means that there's a potential there. So if you have two particles that are attracted to each other, all right, and they start feeling the attraction, they're going to move towards each other. And as they get closer, they're going to speed up. That's energy being transferred from potential into kinetic. It's causing that motion. Likewise, if you've got two things that repel each other, right, as they move closer, the repulsion builds until it forces them apart. And that's, again, energy going from a potential repulsion to actually repulsing, translating into kinetic energy. All right, so that's the second thing. The second concept in the kinetic theory of matter. Thank you so much, Ariana. We are hanging in there. We're on the mend. Still have some symptoms, but a little bit better every day. And naps definitely help. Okay. So the second thing, that's the second thing. Third thing. So the velocity i.e. the speed of particles of matter determine the kinetic energy. So the amount of kinetic energy in a sample is determined by the speed of its particles, right? How fast they're moving. That should make sense. Fourth, particle velocity increases with temperature. All right. So in other words, higher temperatures equal higher kinetic energy, right? Because the higher the temperature is, the faster the particles of matter are moving, and the more motion, the more kinetic energy. All right. And fifth and finally, energy is transferred through collisions. And this this makes sense when you think about it. If you have something that's very hot and something that's very cold, the warm thing is not going to warm up the cold thing unless they come into contact with each other, right? So energy is transferred through that contact. And when we're looking at matter on the molecular level, it's contact in between individual particles bumping into each other. That is how energy is transferred. And that's how you warm up a cold thing, right? You bring it into contact with something that has a high kinetic energy. All right, now, that is the kinetic theory of matter, and that provides kind of a conceptual backdrop for the rest of this chapter as we discuss phases of matter. All right, which we're going to spend a moment on right now. All right, phases of matter. So, as we know, we have the solid phase, the liquid phase, and the gas phase. Right, we've got solids, we've got liquids, and we have gases. And we're going to take a moment to compare the volume / shape of these phases, their density, their compressibility. Do they compress? And their thermal expansion. All right, and when we talk about the solid phase, all right, the solid phase, when it comes to its volume and shape, it is definite. Solids have a definite volume and they have a definite shape. All right, solids have a definite volume and a definite shape. If you have a solid object, its volume isn't going to change, its shape isn't going to change. This is contrasted with the gas phase. Gases do not have a definite volume. They will expand to fit whatever shape you store them in. Expand or compress, I should say. So for a gas, it has an indefinite volume. As well as an indefinite shape. All right, now liquids, this is going to be Goldilocks and the Three Bears here with all of these categories. Liquids is going to be the one that's like in the middle, the one that's just right, whatever that means. Liquids do have a definite volume. The volume of a liquid does not change. So definite volume for liquids. But the shape of a liquid is indefinite, right? If you pour a liquid from a glass pitcher into a glass or into a plastic water bottle, the shape of that liquid will change depending upon the container that's storing it. So liquids have a definite volume. The volume hasn't changed. It's the same amount of liquid no matter what's holding it. But the shape is indefinite, right? It will morph to the shape of the container that it's in. When it comes to density, solids are, the solid phase is a high density phase of matter. And it will come as no surprise that the gas phase is a low density phase, right? And that's Um, that's common sense. If you took here's a Snapple cap, which is definitely a solid, right? And I drop it, it drops down below the gas of the atmosphere. That's because it has a higher density than the gas. Liquids, you may be expecting the liquids to be like, oh, this is a medium density thing. Liquids tend to be high density as well, so they kind of side with solids a little more than gases. Liquids are, relatively speaking, high. The liquid phase is a high density phase. Now, when you look at compressibility, can you take a phase of matter and squeeze it, change its volume? It's going to come as no surprise that the solid phase has a very low compressibility, and actually, the liquid phase as well has a very low compressibility. It's a little bit, but not a ton. The gas phase is a very highly compressible phase, and that's why if you go down to the grocery store and get a balloon filled up with helium, that's compressed helium gas. There's actually a lot of helium stored in that container because it's been compressed down to a small volume. Now, finally, when you talk about thermal expansion, that's how much does the volume change with changing temperatures. Now, all matter will expand as you heat it up. But for the solid phase has a very low thermal expansion. It's still there, and that's why they put cracks in the concrete, right? You'll walking down the side of the road, whenever you see concrete poured, you see those lines through it. If those weren't there, it would expand during summer when things heat up and the concrete would crack. So that's the reason why they're there, to allow it to move a little bit. But if you look at those kind of lines in the concrete, they're not very big. They're very small. That's because there's a very low thermal expansion in the solid phase. The liquid phase does have some, but it is also low. And now the gas phase experiences moderate thermal expansion. So if you heat up a sample of gas, it will expand, assuming that it's not in a rigid container, in which case it won't. All right, so this is kind of a general kind of introduction, some of the different things, categories, quantities that we consider when we're considering different phases of matter. We are going to take a moment right now and focus on the gas phase. For the bulk of the chapter, this is by far the most interesting phase of matter, at least from an introductory chemistry perspective. And so we're going to spend some time digging into the gas phase. And then we'll circle back around and start and talk about phase transitions near the end of the chapter. So let's talk about the gas phase. All right. So when we talk about the gas phase, there are several, when you talk about any phase of matter, and you're talking about sample sizes of matter, etc., there are several different quantities that you can look at when describing each phase. For example, as we just saw, you can talk about the volume of a phase of matter, right? Units for volume are, let me write the whole thing out. Units for volume are liters. You could talk about the moles in a sample. Like if you have a sample of a solid, liquid, or gas, you could say I've got 5 moles, right? So you could talk about you could measure a quantity of matter with the moles, right? And the units for moles are moles. Um, and you could also talk about the temperature of a sample of matter. And temperature units, excuse me, come in degrees Fahrenheit, degrees Celsius, or Kelvin. Kelvin is the unit that we're going to be relying the most heavily on in this discussion. And really, you can talk about the volume, the moles, or temperature of any phase of matter, right? These are pretty unique to every phase. There's one quantity that is pretty much unique to the gas phase, and that is pressure. We don't really talk about the pressure exerted by a solid. Likewise, you don't normally talk about the pressure exerted by a liquid. Now, liquids do exert pressure. In every submarine movie ever made, there's always a scene where the submarine's losing power, like the reactor's failing, and the sub starts sinking right down in the water, and they're getting close to hull crush depth, right? And they're like, oh no, we can't get to hull crush depth, but then the engine turns on and they get away. Hull crush depth is that that depth in the ocean where the pressure of the water, of the ocean water above, becomes so great that it will crush the metal exterior of a submarine. So liquids can and do exert pressure. However, in most contexts, especially most chemical contexts, they don't. They can in geophysics, for example, when you start like studying deep ocean, but unless you're a deep ocean chemist, they're out there, you don't really run into situations where you're worried about the pressure exerted by a liquid. So, very Magic School Bus. Yes, if you were on there, you might want to worry about the pressure exerted by the ocean. So that being said, pressure is pretty, when we talk about pressure, it's pretty unique to the gas phase. Pressure is abbreviated with a capital P. And we are going to spend the next part of lecture exploring the relationship of pressure to these different quantities, to volume, the volume of a sample, to the moles of a sample, to the temperature of a sample. But before we do, we need to talk for a moment about the units for pressure. All right, so let's talk about pressure units. The metric unit for pressure is the atmosphere. All right, in an atmosphere, it's abbreviated ATM. And that is the pressure exerted by the atmosphere of Earth at sea level. So if you're wondering what one atmosphere pressure feels like, you're sitting under one, roughly. If you are at a higher elevation up in the mountains, it'll be slightly less than one atmosphere, but that's one atmosphere pressure. We bear that weight on our shoulders every day. Atmosphere is not the only pressure unit. There are several others. So one, and I would recommend putting these on your exam sheet. Not for exam 2, won't have any of the gas law stuff on it, but for the future. One atmosphere pressure is equal to 760 torr. torr is a common pressure unit. Another common pressure unit is millimeters of mercury. 1 atmosphere is 760 millimeters of mercury. And yes, if you're wondering, 1 torr is 1 millimeter of mercury. You're like, why do they have 2 units that are actually the same unit? They were developed in different contexts, and then it was realized later that 1 torr and 1 millimeter of mercury actually measured the same thing. So that's how we get 2 units that are the same unit. It's a happy coincidence. Another common pressure unit is pounds per square inch. This one is not used as frequently in a chemical context, but in engineering context, it is very common. PSI 14.7. PSI, something to be aware of is these unit conversions, atmospheres to torr, atmospheres to millimeters of mercury, torr to millimeters of mercury. These are all exact. So they do not limit your sig figs. But this one right here, atmosphere to pounds per square inch. Pounds per square inch is an English unit. So this is measured. So this unit conversion has 3 sig figs. So that's important to keep in mind when you use these in your calculations. All right. So now that we've talked about the units of pressure, let's begin exploring how the pressure of a gas is related to its temperature, the moles in the sample, and its volume. All right, so if you were to ask a physicist, what is pressure? They would tell you that pressure is equal to a force applied over an area. All right, it's a force applied over an area. And even though we're not going to do math with this equation, I want to include it here because I think it helps illustrate what we're dealing with here. So pressure is equal to force over area. And if you're wondering, okay, well, what force does a gas exert? Or how does a gas exert force? It exerts force through collisions. All right? That is how a gas exerts pressure. All right? So you think about the gas floating around in this room. The trillions and trillions of particles are all constantly hitting me, bouncing off my face, hitting my camera, bouncing off the camera. They're not just going back and forth. They're going all over this room, all over. And every single little ping, 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 ping of every gas molecule, those tiny microscopic collisions, submicroscopic collisions, each exerts a little force, and each little force adds up to the pressure exerted by the gas. All right? That's where the pressure of a gas comes from. It's through all those little collisions, again, tying back into the kinetic theory of matter. Now, with that in mind, let's explore the relationship between the pressure of a gas and its volume. All right, pressure and volume. All right, so to do this, I want to do a thought experiment with you. Consider 2 samples of gas. I'm going to call the first one sample A, and the second one I'm going to call sample B. All right, and we're going to say in each sample, we're going to say there's 3 moles of gas bumping around, represented by a dot each. Each one, sample A, is at 25 degrees Celsius. Sample B, also at 25 degrees Celsius. All right, so same temperature, same amount of gas in each one. You can see the only difference between the 2 sample sizes, the only difference is the volume of the container that's being that it's being stored in. So the question is, which sample experiences more collisions? All right, sample A or sample B? Well, when you look at it, when you think about it, everything's the same energy. They're moving at the same speed, but because B is such a smaller container, there's going to be more collisions between particles, right? Because the particles are closer together. There's a greater chance of them hitting each other. But there's also going to be a greater number of collisions between the particles and the wall of the container itself. So sample B will have a much higher collision rate than sample A, and as a result, sample B will have a higher pressure. Because more collisions equals a higher pressure. All right, so sample B has more collisions, and because it has more collisions, it has a higher pressure. Now, this brings us to, this allows us to derive a relationship between the pressure of a gas and its volume. So the pressure of a gas, you'll notice that the sample with a smaller volume has a higher pressure. All right, so we say that the pressure of a gas is inversely proportional to its volume. The way you show inverse proportionality is you put that variable in the denominator. So we put volume in our denominator. Now this symbol right here, if you're unfamiliar with this, this is the Greek letter alpha. Spelled A-L-P-H-A. So it's a Greek letter alpha, and it means, this symbol means proportional to. All right, so pressure is proportional to 1 over volume, and that is because the reason why we have volume in the denominator is if volume decreases, if your denominator gets smaller, then your pressure gets larger. If your denominator gets bigger, your pressure gets smaller. So it's an inverse proportionality. All right. Now, the thing is, alpha proportional to does not mean equals. It's not an equals sign. It's not a mathematical symbol. And the reason for that is pressure and volume have different units. So we can't say they're equal because they're measured in different quantities. We at least can't say they're equal as it's currently written. We can, however, say that they are equal if we multiply one side of this expression by a constant number, which I'm just going to call C. If we multiply this by a constant, then we can write this as a mathematical expression, all right? And you may be wondering, well, what is that constant number that we multiplied by this expression? Well, let's solve for it algebraically. Let's multiply both sides by volume. Here, volume would cancel out of the denominator, giving us the expression pressure. The pressure of a gas times the volume of a gas is equal to some constant number, C. All right. Now you may be going, well, Josh, I wanted to know what that constant was, and I still don't. Now I just have it isolated on one side. I don't know what it equals. And here's what I'm going to say in response. The identity of the constant does not matter. It doesn't matter. Here's why. Let's say you have a gas at some initial pressure. We'll call it P1. And at this pressure, it has a volume. We'll say the volume is V1, and you multiply P1 and V1 together. You multiply them together. What does that equal? Well, I don't know, but it's going to equal that constant number, C, right? C is a constant, so its value doesn't change. Well, now let's say the pressure of your gas changes. Now it's P2. Some new pressure, and because the pressure changed, the volume of the gas changed as well. So some new volume, V2, and you multiply P2 and V2 together. What does that equal? Well, it equals that constant number that we don't know, right? This, this thing right here is just a constant number. Now check this out. We don't know what that constant number is, but we know when we multiplied P1 times V1, it equals that constant number. And when we multiply P2 times V2, it equals that constant number. So we don't need to know what that constant number is in order to use this equation. The initial pressure of a gas times the volume of a gas is equal to the final pressure of the gas times the final volume of that gas. And this equation we can use to do examples like the following. All right. So let's see where we're, okay, like the following example. At 1.3 atmospheres of pressure, a sample of gas has a volume of 4.0 liters. What will the pressure of the sample become if the volume changes to 2.5 liters. Right? Now you'll notice in this problem that so first off, first thing you always want to identify is what are you trying to find? And we are trying to find what will the pressure become. So we're trying to find the final pressure of our gas. When you look at what we're given the initial pressure. Initial pressure is 1.3 atmospheres. We're given an initial volume. V1 is equal to 4.0 liters. And we're given a final volume, V2, which is 2.5 liters. All right, so we have also, part of our given information, the equation that relates all of these things together. P1 times V1 equals P2 times V2. We can solve for our final pressure if we divide both sides by our final volume. So we get final pressure is equal to initial pressure times initial volume over final volume. And now we have all of these quantities, so we just need to plug them in. Our initial pressure is 1.3 atmospheres. Initial volume was 4.0 liters. And final volume is 2.5 liters. All right, and now I need my phone to crunch these numbers. So 1.3 times 4 divided by 2.5 is giving me, let's open a new slide. Our final pressure is 2.08. One of the things you'll notice, though, is every value we've been given has 2 sig figs, so we're limited to 2. 8's going to round up. So P2 is equal to 2.1 liters. No, not liters. Liters cancel. We're finding a pressure. This unit is in atmospheres. So that is the final um, the final pressure for this sample of gas. All right. And that is how the pressure of a gas relates to its volume. Let's take a look at how, oops, there we go, how the pressure of a gas relates to its temperature. All right. So pressure and temperature, you're going to recognize a familiar approach to analyzing this situation. So we're going to have what I'm calling sample A, which has 3 moles of gas, compared to sample B, which is being stored in a box of the same volume. I'm not a good enough artist to draw. Oh, wait, here, hang on. I was like, I'm not a good enough artist to draw 2 things that are identical. That's true. But I also have copy paste, which I didn't in previous classes. Oh, wait. There we go. Now, for the first time in any class I've taught, we have 2 exactly identical boxes. I'm going to call this sample B. Same volume, same amount of moles in each sample. The only difference between these 2 is sample A is at 25 degrees Celsius. Sample B, 25 degrees Celsius is like room temperature. It's like in the 70s. Sample B, 100 degrees Celsius, which is when water boils. So that's 212 degrees Fahrenheit. Now, let me pose a familiar question. Which sample has more collisions? All right, which sample has more collisions? Well, hopefully everybody at home is shouting out in excitement and enthusiasm. B, sample B has more collisions. And it's easy to understand, right? If it's at a higher temperature, the gas particles in sample B are moving around much faster, so there's going to be a lot more collisions, both between other gas particles and between the walls of the container itself. So B has more collisions, which means B also has a higher pressure. Because more collisions means higher pressure. All right. So, with that, hang on. There we go. So now that we can see that the pressure of a gas increases with temperature, that allows us to write the following expression. The pressure of a sample of gas is directly proportional to its temperature. Now again, we can't write an equal sign yet because pressure and temperature have different units, right? So pressure does not equal temperature, but we can say they are directly proportional. If we want to write this as an equal sign, we can say pressure is equal to the temperature of a gas times a constant number C. And if you want to know what that constant number C is, well, we can solve for it algebraically when we multiply both sides of this equation by temperature. All right, so this gives us pressure divided by temperature is equal to a constant number C. All right, there is a constant number C. All right, now, what is that constant number? Just like I said before, I'm going to say the same thing back. It doesn't actually matter. It doesn't matter because if you took, you had a sample of gas at an initial pressure, call it P1, that had an initial temperature T1, you divide 1 by the other. P1 divided by T1 is going to be equal to whatever that constant number is. And if your pressure changes, it becomes P2. Your temperature is going to change with it. And when you divide one by the other, it's still going to be equal to that constant number, giving us the following equation. P1 over T1 is equal to P2 over T2. And we can use this equation to solve another set of problems where pressure and temperature are both changing together. Let's do an example. All right. An example like the following. A sample of gas at 25 degrees Celsius has a pressure of 4.81 atmospheres. What pressure will this sample have if its temperature is increased to 98 degrees Celsius? Okay. So, first order of business, what are we trying to find? And we are trying to find our final pressure. When you look at what we're given excuse me, our initial pressure, right, 4.81 atmospheres. We're given our initial temperature, for an initial temperature 25 degrees Celsius. We're given our final temperature, which is 98 degrees Celsius. Now, this looks like we're primed and ready to go, right? This looks like we're all ready to do, okay, P1 over T1 is equal to P2 over T2, because we have P1, T1, and T2, so we can solve for P2. And we do, all of that's true, but we're not quite ready to do it yet. There's one wrinkle whenever you're using temperature in one of these gas problems, all right? Here's the thing that you got to burn into your memory. Temperature must be in Kelvin. Whenever you're using a gas law, the temperature must be in Kelvin. And the conversion from degrees Celsius to Kelvin is you have to add 273. Whatever your temperature is in Celsius, add 273 and that'll convert it to Kelvin. And we have to do this before we can algebraically solve for our pressure. So we need to add 273 to both of these values. So T1, 25 plus 273 is 298 Kelvin. T2 is 98 plus 273, which is 371 Kelvin. You'll notice with sig figs, both of these numbers have their last significant digit in the ones place, as is our answer, so we don't need to round. This number has 3 sig figs. Same with T2, the last significant digit for both of these numbers is in the ones place. The answer has its last significant digit in the ones place, so we don't need to round or anything. All right, now that we've converted our temperature to Kelvin, we are more than able to solve for P2. First step is we need to multiply both sides of this equation by T2. So we isolate final pressure on one side of this expression. Final pressure is equal to initial pressure times final temperature over initial temperature. All right, and now we can plug in our values. Our final pressure will be equal to our initial pressure, which is 4.81 atmospheres, times our final temperature, which is 371 Kelvin, divided by our initial temperature, which is 298 Kelvin. Kelvin cancels Kelvin. We're left with atmospheres, which is good because we're solving for a pressure unit. All right, so 4.81 times 371 divided by 298. My calculator is telling me the pressure is 5.9882 8859. But we can only keep, excuse me, 3 significant digits, 1, 2, 3. This 8 will round up. So our final pressure will be 5.99 atmospheres. Alrighty. So that is how the pressure of a sample of gas relates to its temperature, leaving us with one last relationship to explore, and that is the pressure of a sample of gas, how the pressure of a sample of gas relates to the moles of gas in that sample. So pressure and moles. Okay. Excuse me. So I'm actually going to do the same thing. So we get an exact replica of our box. So we've got 2 samples of gas. 2 samples of gas. Calling the first one A. Calling the second one B. Both of them are at the same temperature, 25 degrees Celsius, which is roughly room temperature. Sample A, they both have the same volume. Sample A has 3 moles of gas. Sample B has 9. So when we pose the question, which is more collisions, the answer should come back as a resounding B. B has more collisions because there's just a lot more gas in there. They're at the same temperature, same volume, but there's way more particles in B. So B will have more collisions and a higher pressure to boot. All right, so the pressure of sample B is higher because there are more particles of gas present, creating all the disturbance. All right, so you can see that the pressure of your gas is directly proportional to the moles of gas present in that sample. All right, now you've seen me do this magic trick before. You know what's going down, right? You know that the pressure of a sample of gas equals the moles in that sample times a constant number C. You also know that we could solve for that constant algebraically, giving us the expression the pressure of a gas divided by its moles is equal to the constant number C. And you're like, we already know what you're going to do. If you have an initial pressure with an initial number of moles, you divide one by the other. It's going to equal that value, that constant. And if you add moles to the sample or take moles away from the sample, if the moles of the sample change, the pressure of that sample will change with it, so that dividing pressure by moles will equal the constant number C, giving us a new expression, P2 over, P1 over N1 is equal to P2 over N2. And this allows us to solve problems like the following. 0.512 moles of gas has a pressure of 3.01 atmospheres. The moles of gas increased so that the pressure is now 5.04 atmospheres. How many moles are now in the sample? Question mark. All right, how many moles are in the sample? Now, sorry about that. I meant to open a new slide, not blank out our last one. So we want to find our final moles, right? All right, so I'm so sorry. I hear my 2-year-old screaming and my 9-year-old doing who knows what. I'm gonna be right back. All right, sorry about that. My wife was upstairs vacuuming, and our 9-year-old was watching our 2-year-old. Okay, but Mom's it's all good now. Mom's on the case. Okay, so we need to find our final number of moles, and we've been given oh wait, hang on. It sounds like alrighty, sorry about that. Hopefully things are good now. So, we're trying to find our final quantity of moles, and we've been given our initial quantity, right, N1, .512, and we've been given our initial pressure, which is 3.01 atmospheres. And we've been also given our final pressure, P2, which is 5.04 atmospheres. All right, so we have all the components to be able to solve, right? P1 over N1 is equal to P2 over N2. So first, this is going to take a little bit more algebra than the other examples we've done today, because the first order of business is to get our final quantity of moles out of the denominator. All right, so this will be final moles times initial pressure over initial moles is equal to final pressure. All right, and now we can solve for our final quantity of moles if we multiply both sides by initial moles over initial pressure. P1 cancels, N1 cancels, and we get N2 is equal to P2 over N1, sorry, P2 times N1 over P1. All right, and now we can use this expression. I'm just going to rewrite it here. N2 is equal to P2 times N1 over P1. Now we can punch in all of our values. So our final pressure is 5.04 atm times 0.512 moles over 3.01 atmospheres. You'll notice that atmospheres cancel. And now we can crunch our numbers. 5.04 times 0.512 divided by 3.01. So our final quantity of moles is equal to 0.8573023. We can only keep 3 sig figs, right? All of these values have 3 significant digits. So 1, 2, 3. This 3 is going to round down. And our final quantity of moles then will be 0.857. And that is our answer. All right. So that's going to do it for lecture tonight. We're still finished about 5 minutes early, but the next topic is going to take a little more time. So we're going to hold off till then. So anyways, that does it for tonight. I'll catch some of you in lab. It's just kind of like an open office hours type of a deal tonight. All right. See you in a few.